Hi, it's Mr. Duffy. Welcome to physics. For today's lesson, we're going to be talking about vertically launched projectiles. And specifically, these are sometimes called ground to ground problems because the object starts on the ground, launches up, comes back down, and lands on the ground again. Um, you're going to see some similarities between our previous lessons on horizontally launched projectiles. You're going to be using a lot of the same equations. But here we're going to be having to watch for our directions a little bit more because we have vertical positive and negative vertical motion versus in the last lessons we just had negative vertical motion. So let's go ahead and get started. So at this point in time in this lesson on projectiles, when I'm going to do some example problems, you should have already done this projectiles relationship lab. And in which case, again, we were looking at how different variables affected the range, how far the object went when it was launched. So hopefully at this point in time, you can answer these questions. Um, when we held the angle constant, what affected the distance that was traveled? Hopefully you thought about that and answered, well, that's going to be the speed at which it was launched. How fast was it going when it was launched? The angle is constant. How fast it's going is going to affect how far it's going to travel. Well, what would be the opposite of that? If the speed was else constant, what is going to affect how far the distance traveled? And hopefully, after you thought about that question a little bit, it's really just the opposite of the first. The angle is what's going to affect how far it's going to travel. Hopefully, you found out that there was a maximum angle that you know caused the object to travel the furthest, and that would be launched at a 45-degree angle. So if an object's launched at a 45-degree angle, you're going to get the furthest distance traveled, the furthest range. Now let's solve for some of that stuff mathematically. Here are some things to kind of watch out for when you're doing vertically launched projectiles or upwardly launched. The acceleration due to gravity is going up and it's coming down. When object is going up, it's being slowed down by gravity, and as it's coming back down, it's being accelerated again by gravity, speeding up by gravity. But the whole entire time, it's negative 9.81 meters per second squared. So whether it's going up or going down, the acceleration is the same, which means the speed it loses going up is the same as the speed it gains going back down. Basically, again, the upwards motion and downwards motion are identical to each other, except for the direction is changing. Okay, so that's again the problems can be kind of divided in half if you want to think of it that way. Finally, the projectile hits the ground with the same speed at which it was launched and projected up initially. So the initial speed is equal to the final speed. Again, the only difference is the direction. Magnitude is the same, the direction has changed. Vertical, positive up versus negative down at the end. Keep this in mind. I had this slide up here when we talked about horizontally launched projectiles as well. The horizontal motion is completely independent of the vertical motion. It has not changed whether, again, it's a vertically launched object or a horizontally launched object. The horizontal motion is constant motion, okay? It's not being accelerated by anything. Just continuing the same velocity the whole entire trip, displacement over time. The vertical motion is accelerating by the value of gravity, okay? Depending on what the problem gives you, determines what equations you're going to use. You're going to find final velocities or displacements, maybe heights, maybe, again, you don't have time, so you, again, have a displacement. You could use the last one. Depending on what the problem gives you, you have to use one of the equations that has acceleration in it. So one of the one-dimensional kinematic equations. Again, I will reassert that with vertically launched projectiles, you have to keep in mind the positives and negatives. Positive is up and negative is down. That's going to allow you to solve for these problems for vertically launched. We did not have to worry about that very much when we had just downward motion, but now we will. So that's kind of the basics of, again, upwardly launched projectiles. The only way we can really kind of like practice them is to do some problems. There are three types of problems that you're going to kind of see when you see vertically launched projectiles. Question is, how far did it go? That's this first question. How far did it go? Another one is how high did it get into the air? That's our next question. And then the final question would be how how hard was it kicked initially? Okay, what would be the initial velocity of the object? Okay, so with those three types of questions, we're going to do one of each of those types of questions. Um, follow along with me, and here we're going to start with one about the range. An elastic loaded balloon launcher fires balloons at an angle of 38 degrees north of east from the surface of the ground. If the initial velocity is 25 meters per second, how far away are the balloons going to land from the launcher when they hit the ground again? So, just like any kinematic equation, any problem, I would start off by listing um, what does the problem give me? And so the first thing it gives me is it gives me an angle. So it gives me an angle of 38 degrees north of east. Okay, the next thing it gives me is a velocity initial. That's 25 meters per second. And then it wants to know a displacement in the x direction specifically. Okay, I would like to write, so again, that's the information it gives me. I would like to draw a diagram of this as well. That'd be the next step. I guess I also forgot to say that acceleration in the y direction would be negative 9.81 meters per second. Yeah, that's right. That is definitely true. It's being accelerated due to gravity. So I'd like to draw myself a diagram. This is the balloon launcher, and it has an initial velocity of 25 meters per second. Not 25 meters per second horizontally or vertically, it's at an angle. The angle is 38 degrees north of east. So I'm going to just do maybe this is the ground, which would again essentially be east. And we're going to go 38 degrees north of it. That angle right there is 38 degrees. I'll just extend that back. Now, we want to know how far it's going to go horizontally. What that's going to require us to do is we need to find the horizontal and vertical components of this vector. So again, this vector is moving at an angle. So it has some x component and some y component that contribute to its overall motion. We need to solve for the velocity in the x. We need to solve for the velocity in the y to be able to solve for how far it's going to go. The velocity in the x direction is going to allow us to solve for the overall displacement, the overall how far it went, the range. So that would be represented by the equation, again, velocity equals displacement over time. We're looking for the displacement, so that would eventually transfer into velocity times time equals our displacement, our range horizontally. Now, again, we can solve for our velocity in the x direction using some trigonometry. We have the adjacent side and we have the hypotenuse and an angle. We'd be able to solve for that, again, using trig. But we wouldn't have time. So that's where the y component of its motion is going to come into play. We are going to have to solve for the velocity in the x and the velocity in the y to be able to solve for this problem. So let's do that next. So I just wanted to kind of show you that the velocity in the x is going to be important to figure out the range, but we do also need to find the velocity in the y. So you might as well just go ahead and find both of them to start off with. Let's go ahead and solve for the velocity in the x. The velocity in the x is the cosine. So we have cosine of 38 degrees is equal to my adjacent, which is velocity in the x, over 25, which is my hypotenuse. The velocity in the y is opposite, so I have sine of 38 is equal to velocity in the y over 25. Okay, let's go ahead and solve those. Cosine of 38 times 25 is 19.7. So this is 19.7 meters per second. I'll write it up here as well. And the velocity in the y is your sine of 38 degrees times 25. It's 15.4. Okay. So we can kind of we can plug this in a little bit here. I just solved for the velocity in the x direction. So the velocity in the x direction is 19.7, and that's going to stay constant the whole entire time of the trip. So that's velocity in the x direction, 19.7 times the time, but we just don't have the time yet. That's where we're going to have to use the velocity in the y. The velocity in the y is going to determine our um, time overall, and our time vertically is going to equal our time horizontally. So let's go back to the last slide. We need to have one that has velocity initial, sorry, yeah, velocity initial, acceleration, and time in it. We don't have a distance given to us, so we couldn't really use it. So the best answer to use for our problem would be this one. Velocity final, velocity initial, acceleration, and time. So let's take a look at this. The velocity initial, again, we're talking about just the vertical portion of its motion. Velocity initial, the vertical portion in the y direction, is 15.4 meters per second. Now, if I went back 2 slides, I'd say again, the upward motion is equal to a downward motion. The speed it was launched at is equal to the speed it landed at. And so I want you to think again that if that's the initial velocity, the final velocity in the y direction is opposite, which just means it's negative 15.4 meters per second. Okay, they have the same speeds vertically, just opposite directions. So that's our initial and our final velocity. We know the acceleration in the y direction is negative 9.81, so we can plug it into our equation. Velocity final equals velocity initial plus acceleration times time. We're going to solve for time here. So our final velocity, negative 15.4. Our initial velocity is 15.4. Acceleration is um, acceleration is negative 9.81, and we're looking for t. So I'm going to subtract 15.4 to the other side. 30.8, negative 30.8 is equal to negative 9.81 t. Divide that by 9.81, and you get time of 3.1 seconds. That's how much time it takes to go up and come back down. Well, that is also the same time it takes to go horizontally. So I can take that information and plug it in right here. So now we have a time, 19.7 times 3.1 seconds is equal to my distance horizontal. And the distance horizontal then comes out to be 61.9 meters. We just solved for the range of the projectile. Okay, the vertical motion determines its time in the air. The horizontal motion determines how far it's going. And again, the combination of both determines how far it's going. Let's look at another problem. A golfer hits a ball at an angle of 25 degrees to the ground. If the golf ball covers a horizontal distance of 301.5 meters, how high did it get vertically? So this is again the second type of problem. There are multiple ways to solve these problems, but let's take a look, and I'm going to show you one of the ways you could do it. So what we have again is an angle given to us of 25 degrees from the ground, so that'd be north of east. If the ball covers the distance of 305 meters, 301.5 meters, how high did it get? We would also know the acceleration due to gravity. Acceleration on the y is negative 9.81. Okay, now I would use a diagram to show this one. So we have ourselves our projectile, our golf ball being hit off the ground, and it kind of comes back down. It's going to cover a total distance of 301.5 meters. We want to know how high did the golf ball get to? Okay, it's fired at an angle of 25 degrees. That does not really look like a 25-degree angle, I agree, but let's just pretend it is. Sorry, I didn't draw that really well to scale. So our question mark is our height. Now, um, there are a variety of ways, again, you could do this, but I would like you to think about what would be the easiest way. What way makes the most sense? Does it make sense to solve for the velocities initial or velocities final? What would make the most sense to do this? And I hope you would kind of realize that the most sense would be just to think about it logically that the upwards motion is equal to a downwards motion. So if we again divide kind of this problem in half, we can imagine that it moves at 301.5 meters totally, but halfway is going to be the highest point in its motion. So half of 301.5 is 150.75. And right at that midpoint is where it's going to be at its highest motion. Well, if we have an angle that it was launched at and we have the adjacent side, why can't we just use that information to solve for the height? That's the answer. This really just comes out to be a trigonometry problem. This one just comes out to be trig. So we want the adjacent, or sorry, the opposite side, and we have the adjacent. That would require tangent. So tangent of 25 degrees is equal to my opposite side, which is my h, over my adjacent, which is 100.75. So let's go ahead and just type that in. Tangent of 25 times 150.75. The height that the ball gets to is 70.3 meters. So this really was not that hard of a math problem. We didn't have to use any of the kinematic equations as we did last time. Um, it's just, again, a thinking problem. Think about what's really going on. Draw yourself a diagram. Hopefully that helps you picture what the motion is doing. And then, again, solve for the height. Okay, there we go. That's our second type of problem. Our final type of problem is finding the initial velocity. So a cannon fires a cannonball 500 meters downrange when set to an angle of 45 degrees. What velocity did the ball leave the cannon? Okay, again, information from the problem. 45-degree angle, 45 degrees northeast. Okay, the range, the displacement in the x direction is equal to 500 meters. Acceleration due to gravity, negative 9.81. We'll see if we need that one again. We didn't need it in the last problem. So the acceleration due to gravity is negative 9.81. I start by drawing myself a picture. I'm going to draw it more as a kind of a triangle. Now I know the projectile does not follow this path, but again, we're resolving things into right triangles for physics. So again, that's the way we can kind of think about it. So we have the upward motion and downwards motion, and they're the same. The total range is 500, but again, I would hope you think that halfway is 250. So each side is 250. This is a 45-degree angle. No, geez, I'm not very good at representing things really well to scale. But if that's a 45-degree angle, then I hope you could realize that the height is also 250 because they would be equal sides, equal angles. 45, 45, 90 triangle. So the height, opposite and adjacent side would be the same. Now, we want to solve for how fast, what the velocity was initially. To do that, we really need to know the time that it was in the air. And the time that it was in the air is determined by the vertical portion. So it went height of 250. So um, we have displacement, we want time. Let's see what we could solve for. I think the first equation is the best again. Velocity initial, velocity final. I think the easiest way to kind of realize this one as well, since you could solve it other ways, since the velocity initial and velocity final would be the same, you could represent them as the same 2x basically. But I think another way to think about it is we have a velocity, just think about it on the way up. The velocity initial is something, and the velocity final on the way up is 0. So when it reaches the top of its motion, the velocity final in the y direction becomes 0. I think that'll be easier to solve the problem as far as like thinking about its motion. So let's velocity final equals velocity initial plus acceleration times time. The velocity initial, we don't know. The velocity final, we know is 0. Okay. Now, the acceleration is negative 9.81. And, sorry, we can't use this one because we don't have, sorry. Velocity final squared equals velocity initial squared plus 2AD. That's going to allow us to solve for the initial velocity. Velocity final, 0 squared equals velocity initial squared, which we don't know, plus 2 times negative 9.81 times d, which is our distance, and that's 250. Okay, so 2 times negative 9.81 times 250 is 4,905. So velocity initial squared equals minus 4,905 equals 0 squared. We're going to subtract. Oh, let's add this to the other side. So then we have 4,905 equals velocity initial squared, square root both sides. And we got ourselves a velocity initial of 70 meters per second. Okay, now that would be the velocity in the y direction initially. But since this is a 45, 45, 90 triangle, that would also be the velocity horizontal as well. So the velocity initial, velocity in the y direction is equal to the velocity in the x direction here. So it was launched initially at 70 meters per second vertically. And since it's a 45, 45, 90 triangle, it was also launched horizontally at 70 meters per second. And then we would want to know, again, the hypotenuse there. So it's a 45, 45, 90 triangle. But also we could use the Pythagorean theorem. So 70 squared plus 70 squared, square root of that is 99, 98.99, so 99. And there's your answer. So that is the velocity that it was initially launched at a 45-degree angle. Now, if this was not launched at a 45-degree angle, the problem would be a little bit more difficult. But what you would amount to is you'd have to, again, use the vertical velocity that we found to eventually solve for the time that it was in the air. And then with that time in the air, you could then solve the horizontal velocity. And then again, you would still solve it at the end the same exact way using the Pythagorean theorem. You'd have the vertical velocity and the horizontal velocity. And again, you could use that a squared plus b squared equals c squared to solve for the hypotenuse of the triangle. So it would be a little bit more work, but still definitely doable. Hopefully, after watching me do these 3 problems, you can see that there are a variety of ways to solve these problems. You might come up with different ways, but still, again, viable ways to solve these. But hopefully, again, you understand a little bit more about vertically launched projectiles. With a little bit more practice, doing more practice problems, you'll be able to solve these in a breeze. Okay, so thank you for watching.